Okay, this is lesson 4.4 on L'Hopital's rule. Back in chapter 2, we used a variety of algebraic methods and tables and graphs to evaluate limits. But in some cases, we can't use algebra like tools like factoring or multiplying by a conjugate to evaluate a limit. And instead, sometimes we can use something called L'Hopital's rule. So let's have a look at two different cases where we could use this rule, and then I'll explain what the rule is. So this first case, we have limit as x approaches, oops, I meant to use my highlighter there, x approaches 1 of ln x over x minus 1. So if I just go ahead and try and plug in 1, we have doesn't really get us anywhere because we'll get ln 1, which is 0, over 1 minus 1, which is also 0. And 0 over 0 is not a defined number, it's undefined. We call it an indeterminate form. We cannot determine what value this function is approaching. Indeterminate. This is one case where we can use L'Hopital's rule, when you get 0 over 0 indeterminate form. Another time you can get 0, or another time you can use L'Hopital's rule is if you get infinity over infinity as an indeterminate form. So let's look at the next case here. Here we're approaching infinity, and we have x squared, which is a function that approaches infinity, and e to the x, which is also a function that approaches infinity as x gets very large. So we don't really know what's going on here. Which function will win out? Which function is the dominant function, the numerator or the denominator? And so this is also an indeterminate form. We don't know the answer, and so we can use L'Hopital's rule for this too. So whenever you get 0 over 0 or infinity over infinity, we can use L'Hopital's rule. And here's L'Hopital's rule. It's shown in the box here. So it says, suppose you have one of the following cases. You get one of those two indeterminate forms I was mentioning before. Then L'Hopital's rule says that for any as x approaches a, f of x over g of x is the same as the limit as x approaches a of the derivatives of those two functions. So let's practice using this. So this one we already know is a 0 over 0 indeterminate form. Notice I'm not writing equals 0 over 0 because nothing can actually equal 0 over 0. We're just approaching this indeterminate form of 0 over 0. So we can use L'Hopital's rule. So L'Hopital's rule says that we can take the same limit as x approaches 1 and do the derivative of each of the numerator and the denominator. And it will give me the same answer for my limit. So the derivative of ln x is 1 over x, and the derivative of x minus 1 is 1. And now I can go ahead and use the direct substitution property and plug in 1 into where the x is, and I get 1. So that is my limit. This function would have a hole actually in the graph at x equals 1, y equals 1. So I'm just going to show you a quick Desmos graph of what that function looks like. Here we go. Okay, so f of x equals ln x over x minus 1. And you can see here when I hover my cursor over the point 1, 1, I see there's a hole in the graph where the function's actually undefined because you can't evaluate the function at that point, but the limit from the left and the right is 1. So we have a hole in the graph there. Okay, let's go back to my notes. Okay, now next one here. This is one we saw above, but it's flipped. So we have the limit as x approaches infinity of e to the x over x squared. So we can see both the numerator and the denominator approach infinity. So we have this infinity over infinity indeterminate form. So this is a case where we would use L'Hopital's rule. So we're going to go ahead and do the same limit as x approaches infinity, but do the derivative of e to the x and the derivative of x squared. So what I get is e to the x over 2x. Now, this is a case where I'm going to have to use L'Hopital's rule twice, because what I see here is that both my numerator and denominator again would approach infinity as x approaches infinity. So I'm going to have to use L'Hopital's rule one more time. So the nice thing about L'Hopital's rule is you can use it again and again if you need to. So this limit is going to be, and this time I won't write the d by dx notation. I'll just do the derivatives. E to the x over 2. Now e to the x approaches infinity. 2 is just a constant, and so this function would approach infinity. I've heard L'Hopital's rule described as like you're trying to figure out which, when you're approaching infinity, if you have a fraction, you're trying to figure out which function, e to the x or x squared, is the dominant function here. Which one is going to grow faster? And then you can determine the overall, what the function is going to do overall. And if you can't determine which one's faster by just comparing the functions, then you can compare the derivatives, because the derivatives, in a sense, are the slope of these functions. So whichever one has a larger slope, that's going to be the one that's growing faster. So if we just take a second to compare those functions, e to the x and x squared, we can see that as x approaches infinity, and I can zoom out here too, right? We can see that e to the x grows a lot faster than x squared does over time. So because that numerator is growing a lot faster than the denominator, overall my function is going to be growing to infinity. Okay, let's do the last one here. Ln x is something that approaches infinity as x approaches infinity, and same with square root x. So we're going to try and see which is dominant, the ln x or the square root x. So again, here we're going to use L'Hopital's rule. Now, the algebra in this one is the trickiest out of the 3 examples I'm doing today. So the derivative of ln x is 1 over x, and the derivative of square root x is 1 over 2 root x. Okay, I'm going to try to write this in a nicer form. Instead of dividing 2 fractions, I am going to multiply by their reciprocals. So, or by the reciprocal of the second fraction. So I'll have 1 over x multiplied with 2 root x over 1. And root x and x can be combined together using exponent laws, so I can subtract their exponents, and I'll end up with limit as x goes to infinity, 2 over root x. Okay, so finally, now that it's in a nicer format, I can look at what's happening to this function as x approaches infinity. So the numerator here is not going to grow, it's just going to be 2, but in the denominator, we're going to be approaching infinity. So when we are dividing by larger and larger values, my function overall is going to be approaching 0. So this is equal to 0. And when I graph this in a second, we should see that there is a horizontal asymptote at y equals 0 for large values of x. So in this case, when the limit is 0, that means the denominator was growing faster than the numerator. So when the denominator grows faster than the numerator, that one is more dominant, and we approach 0. Okay, let's see what's going on with the graphs here. So if I graph these separately, ln x and square root x, we can see that square root x, the one in black, actually I'll change it to a different color so it's easier to see. I'm going to just zoom in on my y-axis here. So we can see that the green function, the square root, is growing faster than the ln x. And if I graph these two together and then zoom out here, we can see that there is it does approach 0 as we approach infinity. Yeah, there is a horizontal asymptote there. Okay, So that is the end of the lesson.